All right, welcome everyone. It's nice to see people from a handful of different um, places, institutions, and this is part of our Collaborative CCCR Speaker Series. We're glad to have Misti Paudel with us today. Dr. Paudel is an assistant professor at Brigham and Women's Hospital. She's a faculty member with the VERITY CCCR. She's an epidemiologist and biostatistician, and her work focuses on difficult to treat RA, but she really applies a lot of different kinds of statistical methods to various topics in the rheumatology space. And so today she's talking with us about ensemble machine learning for risk prediction in rheumatic disease. So I'm thinking we'll have time for questions at the end. Feel free to put things in the chat in the meantime, though, if you would like to do so. I think at the end we'll be able to come off mute and video and talk as well. So, all right, all yours, Misti.
Thank you. I should have time for questions at the end. So hopefully. Anyway, it's an honor to be here. I think this is my first time talking to the group. And I noticed in some of the other presentations you've had, people start with disclosures. So the work I'm presenting today is supported in part by a foundation award that I received, and then through the Verity Methods Core. I also noticed people put a little bit of a disclaimer, so I thought that was cute. I did that as well. I'm an epidemiologist and biostatistician by training, not a data scientist, but I have been very interested in data science methods and how they can be applied within an epidemiological framework. So today I'm looking forward to talking to you about ensemble machine learning approaches, talking through some of the theoretical background and types of output you can get from random survival forest methods is what I'm going to really be focusing on. I'll walk through an example, and it's not an OA example, it's from the rheumatoid arthritis space, but I think if you could focus on how I've applied the methods and how I'm interpreting the results, I think that could be very useful. And then we'll go through some practical considerations when you're thinking about using this method. So let's get into it. Probably the term ensemble machine learning methods can be a little bit different, but what I'm basically talking about is creating many models instead of just one. And the technical definition does talk about aggregating two or more learners, meaning models, to improve prediction. And there's a few different types of ensemble methods, but really it's talked about in two key ways. One is whether it's homogeneous or heterogeneous. By homogeneous, we mean all of the models being trained are basically the same type of model, so that you can think of like a random forest model with multiple decision trees as an example of that. Or heterogeneous, meaning the models can be different. So an example might be combining a decision tree with a support vector machine and a neural network, for example. I'm not going to talk about that today, but I just wanted to throw that out there as an option that in this space. We also like to talk about how the models are trained with ensemble methods. So there's parallel or sequential. Parallel meaning models are trained independently and then the results are aggregated. Sequential means the models are trained sequentially. I'll show you an example of each of those. There is a third that's called stacking, and I won't be talking about that today, but it's different models and then a model to train from the models. Very complicated to think about. Um, really important part of random forest models is bagging or bootstrap aggregating. So this is a homogeneous parallel ensemble method. The process involves training multiple versions of the same model on different random subsets, bootstrap subsets of the data, sampling with replacement, and then aggregating the predictions at the end. So if you have a continuous outcome, that might be involving averaging to get an estimate for each patient, or doing a majority vote if you have a binary outcome, for example. So we see this with random forests and extremely randomized forests and randomized trees. It's really beneficial having the multiple models, and then the effect of all of that random sampling reduces the risk of overfitting. It's pretty robust to noise and outliers in the data, and it's definitely much more stable than one model alone. Boosting, by contrast, this is a homogeneous sequential ensemble method. So this is where you're training models consecutively to try to really hone in on where they're getting the predictions wrong and to fix it. So it involves, creating a model, looking at the output, weighting based on the incorrect predictions, and then continuing to cycle through multiple models, incentivizing the model to get those predictions right. Gradient boosting and XG boosting is probably the two most common examples of this. And as you can think, you would want to use this maybe when your goal is you really want accuracy and you're willing to sacrifice some overfitting to get there. That's when this can really be a benefit. But backing up, I think it's important to talk about decision trees as part of this. So this would be the parallel learning that I've been talking about. The example on the right is from an OA paper. The paper did not use decision trees, but I saw this clinical classification scheme and I thought that really looks like a decision tree. So I put that in there as an example. But the structure of it is that you maybe have, like in this example, population of patients with knee pain. Your root node would be the very first variable that the model selects to start splitting and creating the tree. In this case, it's crepitus, but if you were to apply a decision tree, it may not have picked that. It may pick something else, and we'll talk about why it might do that. And then each subsequential node after the root node is called a decision node. And then you end up at the end with your terminal nodes, and that's where your final predictions are. So random forest is multiple decision trees combined together. So, and the concept really is wisdom of the crowds approach. So the thought is that multiple less robust prediction models combined together can create a much better prediction. Obviously, they have to be predictive. So if you're combining a bunch of models that are not predictive, it's not going to help you in the end. And yes, I've seen that happen. It's very disappointing. But the combined result will hopefully produce a more robust and stable, accurate prediction that would be generalizable. So I will be showing the process a little bit more in depth in the next few slides, but it involves random sampling of patients, random sampling of variables, which in the machine learning world we call features, and then growing all of the different trees and aggregating the predictions. So this randomness of the feature selection is really, really key. It ensures that the trees are not correlated. Randomly sampling patients, randomly sampling predictors. And I'll go through some of this more in other slides, but before you start, as always, to get good quality predictions, you've got to ensure that everything you're throwing in is potentially viable. So a lot of steps I've done in the past are to toss out any variables that are either very low prevalence or very high prevalence, because they're just not going to be useful to you in any prediction. Eliminating any duplication or redundancy, dummy coding if you need to, and only scaling if you need it for interpretability. The good thing about these models is they're pretty robust to that. You don't need to do that. And then, like I said, if none of the features or variables in your model are predictive of your outcome, this isn't going to help you. So getting into this a little bit more detail, when we are building these decision trees, it's using a random selection process of patients, bootstrap samples from the database. And then, like I said, random sample of features. But in this figure, what I'm showing is each tree has a training and a validation set. And you can you can set this, you can tell it what percentage of patients to include in the training versus the validation set. If you don't, the model will just pick usually around 63% is what I've seen. So, for every tree, you want somewhere between 60 and 80% of patients being sampled with replacement. And the benefit of having those little validation sets is you've got data to use for validation later on. How does it pick features or variables at each level of the tree? It's doing this through random draws of the variables that you're telling it can choose from. So, for example, if you have a data set with about 50 different features or variables, you may tell it to draw 7 at each node of the tree that it's building. And that's kind of the general rule of thumb, is the square root of the total number of features, but you can play around with this to get better fitting models. So for example, in this graph I have, maybe it picks like age, gender, pain level, current and prior treatments, morning stiffness, crepitus. It's going to choose the variable that gives it the best split first out of these. And there's 2 ways it does this. It's through the Gini impurity or information gain. Let's quickly look at what those are. Gini impurity, I would say, is usually the default in most of these models because it's pretty quick to do, doesn't require a lot of computation time, and machine learning methods tend to prioritize that. It also gives about the same answer as the other method, which I'll talk about too. So the concept is preserving homogeneity in the terminal tree nodes. So this is really assessing the likelihood of a new observation being misclassified if it were just given a random label according to the outcome, the class distribution in the data set. And I've got the math there, taking 4 examples. I think this is from the web on a credit history, whether to give someone a loan or not, based on age, income, student, and credit rating. In this example, age ended up having the best Gini value, which would be the lowest Gini value of all the variables. But when it's looking at the splits, it's looking at the purity, how many patients with the outcome versus not the outcome are being included. So if you've got 50-50, that variable is not really helping you find people with your outcome. We call that totally impure. It's a coin flip. The best for Gini would be a value of 0. That's where this variable can identify 100% of patients with the outcome, which should be a perfect predictor. We almost never see. Usually the truth is somewhere in between. So that's how it's doing. It's actually very simple math that it's using to do that. Information gain or entropy is another method you can ask it to do, but you usually have to specify because it's computationally a little bit more expensive. And it is really looking at the amount of information or disorder or uncertainty in a system, in this case, in the nodes. So entropy is how much class mixing, again, it's kind of similar to what I said about Gini impurity. Information gain is how much entropy we can remove by doing the split. And I have the example on the right side. I won't go through it, but again, it's very simple math. And the same concept applies of if you've got the variable really just gives you a 50-50 split, it's a coin flip. It's not very useful. You'd have high entropy. If it's giving you perfect prediction, entropy would be 0. So you wouldn't be removing any information if you had a 50-50 split from the model. So a little background. And then I mentioned when we are drawing random samples of patients for each decision tree that we're making in a random forest, that we hold out a subset of patients. We call this the out-of-bag samples. And it's a nice little built-in validation system for random forest models. There's maybe somewhat little bit of of disagreement on whether you still need to split data into training and testing sets when you're developing these. But I think the more general consensus has been when you're using this method, not necessary because it's already building it in for you. Other methods, you probably still need to do that if it's not built in. But, this gives it unseen data for each tree that you can use to check the validation. So again, like I said before, usually you build trees on random draws of 60 to 80% of the sample, which leaves you a nice subset to validate. And then random survival forests, everything I just said still applies, but this is an extension of random forests for right-censored time to event data. So you grow a forest of survival trees. And I've used the random forest SRC package in R. At this time, I don't think there are other packages, but I could be wrong about that. And I am not going to be showing this, but one thing you can do is you can output a risk score too from the model that you can then use to risk stratify. But let's go through an example. Looking at the development and external validation of a predictive model for progression to difficult to treat RA. This was published earlier this year in ACNR, and I did a podcast episode earlier this year on it as well. But I think it's a nice walkthrough of how to apply this method and pros and cons and what we learned. So the concept that I'm very interested in is biologic cycling in RA, and this concept that 1 in 5 patients with rheumatoid arthritis will cycle through multiple therapies without observing substantial benefit in terms of treatment response and symptoms. And accumulating multiple treatment failures over time is a significant challenge for rheumatologists and the patient. To figure out how to effectively manage their care. So there's a definite need to understand the epidemiology and the risk factors for progressing to this, we call it difficult to treat RA disease state. And currently we're unable to really predict which patients are most likely to benefit from particular treatments or which treatment's going to be effective. And we really don't understand which patients are going to cycle through multiple treatments and fail. So my goal at the start of this was to use clinical factors to predict this phenotype of difficult to treat RA. And I'm using a definition proposed by EULAR, which is multi-component and requires that a patient meet 3 criteria at the same time of DMARD failure, persistent disease activity, there's multiple subcomponents there, and perception of a persistent problem, meaning that either the patient or the rheumatologist perceives there to be a problem in managing this patient's care. You have to have one from each criteria. One from each of these categories to qualify as difficult to treat. And it is a heterogeneous mix. So some patients will qualify based on persistent inflammation. Others will qualify maybe persistent symptoms, but not inflammation. So there's a lot of work to be done in the future to kind of parse this down and understand it more. But for starting out, I think this phenotype is really important to stay broad and to better understand these patients. So in the literature, there's been some previously identified risk factors that have been reported. So older age, higher levels of rheumatoid factor, greater disease activity, lower methotrexate dose or non-use, which probably represents failure on methotrexate, hypertension, diabetes, pulmonary disease for comorbidities, longer delays in initial treatment, and obesity. I had 2 data sources to use for this. One was a local registry called the Brigham and Women's Arthritis Sequential Study, BRASS. This is obviously in Boston. Patients that enrolled in this had established RA, annual visits with their rheumatologists, and interim 6-month follow-up questionnaires. For this, I selected patients at the time that they reported being treated with their first biologic. I'll show you a graphic of that. And they weren't currently meeting the definition of difficult to treat at that visit. And there ended up being about 700 patients that met this criteria. I also had access to another data set to validate, and that's called the CERTAIN data, or the Comparative Effectiveness Registry to study therapies for arthritis and inflammatory conditions. It's a sub-study of core Evertas, formerly known as Corona. These patients also had established RA, but they had moderate or higher disease activity when they were enrolled. So a more severe subset of RA patients, and they had to be starting or switching to a biologic. And they had clinic visits every 3 months for up to a year. If they needed to switch, then they were re-enrolled and enrollment started again. So I had to chain those together. But those patients, there are about 2,000 of them. And I tossed out anyone who was difficult to treat RA when they were enrolled. There were a few. The time periods for the two different studies are side by side here. So brass on the left, like I said, multiple years, visits every 6 months, annual visits with a rheumatologist. And my index date starting point for my analysis was the first visit where they reported being treated with their first biologic. That could have happened when they first enrolled in the study, or it could have occurred later on as they transitioned to a biologic. I did this because I wanted a clean data set of patients that were fairly similar to train the model. CERTAIN, however, is very different. So again, they're enrolled at the time that they're switching or initiating a biologic therapy, much shorter follow-up, 12 months. Baseline characteristics, these are all pretty classic for RA cohorts between the two data sets. Things I will point out where things are quite different between the data sets would be the first row of follow-up months. So brass, much longer follow-up, a mean of 83 months, compared to CERTAIN in the full sample was about 8 months. And I did split out patients that were biologic naive subset, because that would be more similar to my brass cohort. Other ways they were a little bit different was, like I said, the disease activity. So CDAI greater than 10, about 58% of brass patients had moderate to severe disease activity compared to, well, it was all in CERTAIN. It comes out to be 99% depending on which measure they're screening versus enrollment that they're picking. And then pain scores were also higher in CERTAIN as well. So important to keep that in mind. My analytic pipeline involved, first doing some data cleaning, removing outliers, things like that. There was some missing data in brass, so I did imputation. And the nice part about random survival forest is it has an impute mode. So you can impute variables very easily, taking all the power of all those decision trees and aggregating them. I also went through a process of trying to tune the model. We'll talk about that a little bit more, and evaluating its performance. I did end up trying to improve it by removing some of the variables or features that were not helpful for the prediction. It's something that you really want to do very carefully and thoughtfully. In my case, it did help improve the model. And then looking at measures of discrimination and calibration, and then testing the model out in the CERTAIN data as an external validation. So here's some results. So for brass, I ended up having 23 features or variables that I could include in the model. I started out with more than that, but like I said, I eliminated any of the ones that were not helpful for the prediction. And it ended up being, 16 clinical factors, 5 patient-reported outcomes, and about 2 treatment categories that remained. Out of the 700 patients in BRASS, 113 of them progressed to difficult to treat RA. I created 1,000 different decision trees with those 23 variables. The resample size to grow trees, that's my my bootstrap sampling, how many patients am I randomly sampling each time, is about 63%. M-try is my random sampling of how many variables am I testing at each node of the tree. That ended up staying at 6. That's about, I think, the square root of 20. Maybe square root of the total number of variables is what I started with. I ended up making this to be 6. I ended up observing a Harrell C index of 0.64. So better than chance, but in the world of being able to predict things, maybe a little disappointing if you don't at least hit above a 0.7. When I went to reapply these methods in the certain cohort, I kept all of the assumptions the same. Ended up with C indexes of 0.62 in the full cohort, 0.66 in the naive subset. So it's nice to have pretty similar performance across those 2 data subsets. One of the fun things that you can get out of a random survival forest is the top predictors. And there's a few different ways to show that, but one of the methods that I've grown to kind of really love is this SHAP beesworm plot. These are based off of Shapley values, where these models are run based on every possible combination of variables to get information on how much each variable contributes to the prediction. It gets its basis really in game theory, which is an approximation of how much each player contributes to the outcome. Just kind of a fun reuse of that concept in research. So we apply it in machine learning to really understand the value of each predictor to the model. So how you look at this plot is, they say a picture's worth 1,000 words. I think there's probably an entire paper that could be written from this information, but really from top to bottom, it's organized by highest ranking variable to lowest. So most important variable to least important variable according to its mean SHAP value. Each row has a dot for each participant. So like for the top one, the MD-HAC total, there's 700 dots there, one representing each patient. And the color really represents the feature value. So yellow would have like high values, higher scores if it's a continuous variable, 1 if it's a 1-0 variable. Purple would be lower values. So 0 if it's a 1-0 variable, or lower scores if you're on a continuous variable. The x-axis is your SHAP value risk. So above 0, that variable increases the risk. Below 0, it decreases the risk. Sometimes I think it's easier when you look at the binary variables. So look at methotrexate first. That's about midway through. So you see a bunch of yellow on one side and a bunch of purple. It's a 1-0 variable. So what we saw in the data was that methotrexate use had a lower risk of progression to difficult to treat. So that's why you see the variable, this one seems to be flipped, as opposed to if you look at further down, prednisone use or BMI greater than 30, where you see high, being a 1, having that, being a prednisone user or being obese had a higher risk of progression to difficult to treat. So the yellow being above the SHAP value line. But that's how you interpret it. If a variable is linear, a continuous and a linear association, you'd see a nice ombre or graded color scheme from purple to yellow across the scale. But more mixed kind of sometimes suggests that maybe it's not a linear association with the outcome. So what we observed was really those patient-reported outcomes were the strongest predictors in our data set. So the MD-HAC total score, patient's global activity score of how they thought their disease was, how active they thought their disease was, fatigue, pain, and then we start to get into like C-reactive protein and methotrexate use and things like that. And again, I'm putting those in here, kind of showing that it did differ from the prior literature in some ways, which was perhaps a little bit surprising from this analysis. Another thing you can do is you can look at a plot of prediction error by time. So I'm showing you one from BRASS and one from the full certain study. This is a little bit different way maybe of looking at prediction error. So I've got prediction error on the y-axis and time on the x-axis. The black line is a null model, no predictors, looking at risk of progression to difficult to treat RA. The red would be our random survival forest. So in BRASS, this looks pretty good. We lower prediction error with our model over time, so that's nice. In certain, it gets a little bit wonkier. It kind of suggests maybe because of the time difference, our model may have performed similarly in terms of discrimination, but in terms of predicting the survival time, it wasn't as accurate. So that's where we see the red line surpassing. And then, we're not doing Kaplan-Meier directly in the random survival forest, but we can create the curves by outputting the predicted probabilities at each time point. So this is my Kaplan-Meier-like survival curve from BRASS. And then, to kind of bring this back to something that I do know, our tried and true of Cox proportional hazards, I took the top predictors, plus Forced age, and created a series of Cox proportional hazards models. So this is all unadjusted. These are separate models for each of the variables, and looked at the hazards ratio, and I printed the C index as well for each of the models, just to try to get a sense of am I seeing something in Cox proportional hazards for these as being associated with risk of difficult to treat RA? And the answer is yes. A lot of these are continuous variables, so it looks scale-wise, very small. But for the MD hack, a per unit increase has a hazards of like 2%. That's pretty striking, actually, considering these are pretty broad scales. BMI 30, that one further down, that's got the strongest effect. That's the binary variable of obese versus not obese. So being obese is associated with a 64% increased hazards of progression to difficult to treat RA. So I do see people doing this when they use random forest. They try to take those variables and put them in a Cox to better understand the magnitude of the associations with difficult to treat RA. And I think you can do that. It also kind of highlights why sometimes random forest isn't giving us exactly what we're looking for. It's like we're used to looking at these types of things, and you can't really get this easily from a random forest model. So, when would you use or not use a random survival forest? I'm perhaps going out on a limb with some of these suggestions, but if your goal is just prediction accuracy, you don't really care about looking under the hood and understanding why things are predictive, then random survival forest or other machine learning methods would be a pretty robust approach to your data. If interpretation of those predictors is a must, you have to have inference, you're probably better off with Cox proportional hazards, maybe doing a lasso regression or something if you have a lot of variables to filter out. If you're like my goal, you have a lot of predictors and you really just want to find the top ones, random survival forest turned out to be a really interesting approach to that and helpful. If your sample size is small, probably best to go with Cox proportional hazards. If your proportional hazards assumption is violated, I would say go with, unless you want to model that in your Cox proportional hazards directly, I would say go with random survival forest because it doesn't rely on that assumption at all, which is nice. And again, low event rate, probably better off with Cox. Sometimes random survival forest models can struggle when there's a really low event rate. Um, and then when it comes to interactions, a lot of times you'll read that random survival forest handles the interactions and it's very nice. It's a little bit of misinformation. It's a different way of thinking of it. It's not random survival forest, like I showed you at each node, it's only worried about which variable to pick one node at a time. If it was playing master chess and thinking several nodes ahead and which variables can I combine to get the best prediction, then I would say random survival forest could probably be pretty stellar at looking at interactions, but it's not doing that. It's one node at a time. So if you don't care about interactions, you just want to handle them and make them not a problem, random survival forest is great. If you really want to look at those and model the interactions manually, you've got to do that with Cox proportional hazards. And then if you've got a lot of correlation between different variables, I would suggest random survival forest, unless you're really interested in trying to filter that out using our traditional methods. So I did a quick search in OA research to see what's been done, and I was really specifically focusing on, random survival forests or random forest methods, and I came up with a few papers that I was seeing mostly within the last year or two. Um, it looks like prediction is the main interest. I would say, from what I've read in the literature, a lot of the bulk work that's been happening in machine learning has been on images, reading images, predicting from images. Not as much progress has been made with prediction models, but you do see some work happening, at least in that area. And I finished quite nicely. So that was the end of my talk. So thank you for listening. I'm happy to talk more with people.
Right, thank you very much. We have a bunch of comments or a good handful of comments in the chat. And I don't know, Misty, if you can see those. Do you want me to read them for you? Would that be helpful?
Unless I stop sharing, I don't think I can
Okay,
see
yeah, let
them.
me read them for you in case
Yeah.
others, and that way others can hear too if they can't access the chat. Okay, so
Mhm.
two questions from Ted Jang. Okay, first, can you use a combination of candidate features at each node? So this is going back to earlier in your talk, instead of the best candidate feature. Actually, the second question is pretty separate. So let me have you go ahead and answer that one.
Um, the standard for the models is they're using either that entropy calculation or the Gini impurity calculation to pick the best feature for at each split. Unfortunately, I don't know of a way to specify that differently.
Okay, let me ask this.
Other than to increase the number of variables, maybe that you're having it look through to pick. But.
Yes, maybe this question is a bit of a follow-up. So from both the gain and Gini impurity perspectives,
Mm-hmm.
it seems that the selection of root node is critical and needs to match the goal of the study. For example, it needs to be most clinically important, pain maybe, if the goal is to study clinical outcome, but could be others if the goal is to study OA epidemiology or just epidemiology in general. Is that correct?
Um, I don't know of any literature saying that that's a make or break starting point. I think if you were talking about like when I was explaining some of the other ensemble learning methods, so the sequential one where you have to start with a first model, I've read that that's make or break. Your first model is really important. But when it comes to decision trees, remember you're doing this 1,000 times. It's cycling through and it's creating 1,000 different trees. And that first root node is going to be different depending on which random variables it's picking. So I think the make or break is really making sure you're having enough replications, you're creating enough trees, and you're making that random draw of how many variables it assesses big enough so that you can be confident that it's picking something that's really of value, but not so big so that you're making it look at every single variable and probably overfitting to the data. Um, if that helps. You know.
Any follow-up questions or comments on that point from anyone? Okay, if not, let me go to the next one from Lubov. Can this package handle correlated observations, so joints from the same individual?
Um, I so if you were letting having different joints be put in the model, I have not seen an example of that actually. It would probably treat each patient as observation as independent, which is not what you would want it to do. So no, I would say I don't know of a method to kind of account for that in these. But I'd be interested if anybody else has encountered that.
Any follow-up comments there?
I would be great
Yeah,
to
Caleb.
see sort of a way to incorporate, the individual joints, almost dealing with sort of RA classification,
Yeah,
as we and seeing how the models would turn because it's sort of you would expect it to follow sort of the classification criteria at some level of large joint versus smalls, but which actually might be more contributive to MD hack
yeah.
scores as well. So yeah, that would be a good future project.
It would be. And I bet you could extract enough information out of the model to maybe do that in the back end. Weighting maybe by number of joints or something. I don't know. Just thinking out loud.
Yeah, as somebody who designs questionnaires, one of the concerns we always have is how much of our physical function surveys are weighting toward lower extremities versus upper. And,
Yeah,
getting an idea on the joints being affected would be really nice.
understand. Yes.
I had a question for you about your bee swarm plot, if you could go to that, because I love this figure. And, you know, like you said, pictures of 1,000 words, and there's so much information here. But my question sort of came to looking at this, and I was really surprised at CRP. Um, First of all, how there was very little to know on the high score. So it made me feel like this had a tremendous tail or some outliers on the CRP score.
It probably,
It,
I mean, it looks like for most patients, it really wasn't that helpful, but there was perhaps a subset where it was. Um,
Sort of hidden in the blob somewhere in there.
it's
This,
hidden, yeah.
is this sort of, would it argue for a transformation to sort of see like, or does it not matter in this model?
Um, this method is supposed to be pretty robust so that don't necessarily have to transform the variables. What it's doing when it's picking CRP to split on is it's finding the cut point that it wants that gets it the most difficult to treat RA patients separated out. So it may do that differently. That's important to think about too. With each tree, every time it picks CRP, it may pick a different cut point depending on what's happened above that in the tree.
And it is likely a very
Yeah.
high cut point, maybe in this regard.
It would look like
Interesting.
it. I'm starting to I see a little bit of yellow peaking at the higher values for CRP.
Okay. And
Yeah.
now this as a component of your DAS CRP,
Mhm.
um, is that the correlation there accounted for in this way as well? So it doesn't have the usual negatives for having them all in?
Right. So really one of the fun things with this method is that you don't really have to worry about that so much. So I do have things in here that are highly correlated with each other. And it doesn't matter. It's looking at them all independently every time it's making a split.
Fun. Thank you.
Yeah, yeah.
I see another comment, Lou, that you put in there about an extension called oblique RF. Is that pertaining to the prior question about correlated
Yes.
observations?
Yeah, this is about the first comment about the combination of features. I just saw the extension of standard random forest. When you combine and use linear I never use this, but you know, I was reviewing the paper and they use this.
Oh, that's excellent. Yeah, no, I have not used that
Yeah, I've
either.
never,
Yeah.
and
Yeah.
I didn't review the paper. I declined because I didn't use it before, but it was.
Fair point.
So that gets through the comments in the chat. We have a few more minutes. Others have any comments, questions?
So I have like one technical question. This is again about several observations from the same person. You know, sometimes features, let's say knee related on knee level, and other features are like person level. So do you have any experience with random forest standard or survival with these combinations and how it like um
So yeah, these are all person level,
yeah
not joint level.
yeah I'm just
Yeah,
wondering if you have a lot of person level features, maybe they kind of will drive the conclusions and make knee level features less important. I'm just always wondering if there are like some theoretical work done.
right. Yeah, not that I'm aware of, but
Yeah.
I mean, I really think, especially a joint that's impacting their quality of life, like mobility,
Mm-hmm.
I could see how that would be way more weighing on their reports of pain and everything else
Yeah.
than joints that are not as impactful on their quality of life.
Yeah.
Yeah. But I have not seen that applied.
I had a quick question about, I guess, random forests in general, as well as the survival forests. It's
Mhm.
because it is a multivariable approach to, predict. I do occasionally get questions like, well, is it an adjusted analysis? And that I struggle with trying to answer because it's really not doing an adjustment the way we think of a standard adjustment. How do you
Right.
think about that?
Right. Yeah, no, it is not doing an adjusted analysis. So when I present all of these variables, it's really these are the ones that the model said were the top predictors across all of those all those tree models. So it's not adjusted for anything, not like we would get from a Cox proportional hazard. Hmm.
Any other questions, comments? I don't
have a
see any.
question.
Okay, great. Yes.
In terms of the Shapley value, there's been some argument for the Shapley value, some argument against the Shapley value. What is your argument for using it to understand the results a little bit better?
I have learned to love it because I love this kind of a plot, but I would say I do get a fair amount of pushback from time to time with people saying, I don't know how to read this. This is too much information. Um, I've also seen people use just like a variable importance plot, which is it's very simple. It's one bar for each variable. I didn't put an example in here, but that would be a measure of how important that variable was to the prediction. And it would probably give you the same rank ordering of variables. So I think they both give you pretty similar information. It's just how deep do you want to go into trying to understand the complexity of the SHAP values.
Okay, thank you.
Yeah.
So Misty, there are a few comments in the chat that are just thank yous and appreciation
Oh.
for nice slides, that really nice presentation. Clearly a lot of
Mhm.
interest, really useful. Yeah, I just want to one more time open up for any other comments, questions. All right. Well, thanks. Thanks everybody for being here. Thank you again, Misty. This was great. And hope
Yeah.
to see you all at a future one of these down the line.
Yes.
Thanks, everybody.